Hello everybody, welcome back to another Strengths Materials video. This one is on shear and bending moment diagrams. I'm going to be showing you guys how to solve this problem as if you're working as an engineer and trying to get through it super quickly. And this was actually sent in by one of my subscribers, so I'd like to thank them for sending this in. And I think they had some problems with the fact that there's two free ends on this beam. I'm going to show you that this problem is super similar to the ones that we've done in the past. In the first place that we always need to start with is figuring out what these reactions are. So we pick a reference point at one of these supports. I'm going to take the roller at A. I'm going to set the moment about A equal to 0, pick my sign convention, and get rolling. We have the resultant force that we run into first from the distributed load. So that's going to be negative 5 kilonewtons per meter. That is over a 5-meter length. And that distance from A is half of 5 meters because it is rectangular. The next one we're going to run into is this 30 kilonewtons. So we have 30 kilonewtons. That distance away is 3 meters. The next one we run into is By, which I've drawn downwards, so it's going to be negative. We have By times the distance away, which is 5 meters. And then we have the final force from the 20 kilonewton at the end. So we have a positive 20 kilonewton for that counterclockwise rotation at a distance away of 5 plus 4, which is 9 meters. Then solving for that, By is going to be equal to 5.5 kilonewtons. And that's positive, meaning that we've drawn this in the proper orientation. The next thing we can do is go ahead and do the summation of forces at Fy to figure out what the reaction at A is. So we have Ay first, and then the Fr from the distributed load, which is downwards, which is going to be 5 kilonewtons per meter, times the length it covers, which is 5 meters. We have the 30 kilonewton downwards. We have the By, which is also downwards, so negative 5.5. And then at the end, we have the positive 20 kilonewtons at the end, meaning that when we solve this, Ay is going to be equal to 40.5 kilonewtons. All right, so let's start filling in this diagram. First segment that we're looking at is segment 1. We can see that there's no reactions or forces acting in this segment, so we know that this entire segment is going to be equal to 0 over that length. Moving over to the next spot, we have a jump created by this Ay. So we're going to have a point created at the top here of 40.5 kilonewtons. Then we have this distributed load that we're considering all the way until this 30 kilonewton force. And the way we consider this, taking section 2, we have to consider our rules, right? So the change in shear is going to be the area under a loading curve. So that means we need to figure out what the area is created by this distributed load. That's going to be 5 kilonewtons per meter over 3 meters. And then take the difference between that jump that was created by Ay. So let's see what that looks like. So here's the formula that I am referencing for this. And then solving that, you have 5 kilonewtons per meter over 3 meters until you get to that 30 kilonewton force, because there's going to be a jump there. And solving that, you'll get a value of 15 kilonewtons. That's going to be negative since this is a negative distribution. And then taking the difference between the jump, you have 40.5 minus 15, which is going to give you a value of 25.5 kilonewtons. All right, so now we plotted those points and drew the line between the two. And I know that that line needs to be negative with a constant slope. Why do I know this? I know this because of this rule right here. So my distributed load is a negative with a constant value, meaning that for the shear diagram, it has to also be negative with a constant slope. So that's why I'm going down with this linear line from 40.5 to 25.5. Next part, we go to section 3. We first need to start with this 30 kilonewton force as a jump downwards. That jump downwards is going to be 30 subtracted from 25.5. So we have 25.5 minus 30, which is going to give you a value of 4.5 kilonewtons negative. So it's going to be negative 4.5. Now the next thing we need to do is super similar to what we did up top. We're taking the difference in shear, which is equal to the area of the distributed curve. So we have a 2-meter stretch instead of 3 meters this time. So we're simply going to be following the exact same formula for this section. Alrighty, now we just got to take this away from the existing negative 4.5 that we have. So we have negative 4.5 minus the 10, which is going to leave you with negative 14.5 kilonewtons at the end of segment 3, which is somewhere around here. And same type of thing, we have a negative constant slope for the shear diagram. All right, now that's plugged in. The last segment is going to be started off with this by jump in the downwards direction. So we just need to add 5.5 to the 14.5, obviously both being negative. And when you do that, you're going to be left with a value of 20 kilonewtons negative. And then since there is no other shear forces or forces acting between this point and the end, we're going to be constant with no slope all the way until this 20 kilonewton jump in the opposite direction, which brings us back to 0. Alrighty, so now we can start filling in the moment diagram. I already gave you guys a little bit of a hint for segment 1. We know that since there's no shear developed between this segment, there's also going to be no moment. So that value is going to be 0. So that means we're starting from 0 and figuring out what's happening between the start of segment 2 and the end of segment 2. That's going to be governed by the area underneath this shear diagram. And you can see this in the formula right here. So the difference or the change in moment is going to be equal to the area under the shear diagram. That's represented by this formula right here mathematically. So we're just going to be taking this formula and solving it based on what it's asking for. So we have a triangular shape here, and the difference between that apex and the bottom of the triangle is going to be your height. So that's 40.5 minus 25.5. And then you have the area of the rectangular section of the shear diagram, which is 25.5 kilonewtons as the magnitude or apex of that rectangular shape. So we can start solving for what that area is. We have 1/2 for this triangular segment. The difference is going to be 40.5 minus 25.5. It's going to be in kilonewtons. Then over a distance of what? 3 meters for that segment. And we are also adding for that rectangular segment as well. So there's no coefficient here. It's going to be just 25.5 kilonewtons. That's times 3 meters as well. And that value is going to be 99 kilonewton meter. That's going to be plotted somewhere around here. But what is going on with the slope of this curve? Well, this shear diagram currently has a positive decreasing value. So that means the slope of our moment diagram should also be positive, so over the line, but decreasing. Alrighty, so now it's plotted here. And just to describe this one more time based on the formula, our slope is still in the positive, increasing range. However, the slope is progressively decreasing as we get to this point of 99 at our apex. And then similarly, for segment 2, or for segment 3, sorry, you have something very similar, except now you're going to have a negative value. So we're coming down, and we're going to see that this slope is also increasing. But let's see what that looks like with the numbers first. We have a very similar breakdown to what we did before, where the area under the shear diagram is going to be that difference in moment. We're starting at 4.5, going down, or starting at 14.5 and then going down to 4.5. And this is a triangular shape. And then we have a 4.5 rectangular shape right below it. So that is the area that we're going to be working with. And solving for this, you have a value of negative 19 kilonewtons per meter. And then we're taking this away from that original value that we had in the previous segment. So 99 minus 19 is going to equal to 80 kilonewton per meter, or kilonewton meter. Excuse my French. So we're going to plot this here. And once again, we're going to have a curve that looks something like this, where the slope is going to be increasing, but it's negative, so it's going downwards. So that brings us to look something like this. Alrighty, so I applied that third segment, and I've also gone ahead and done the fourth segment because it's fairly simple. You're going to have that 20 kilonewton magnitude for this shear area, and then over a 4 meter distance. That's going to give you 80 kilonewtons, and then this shear plot is going to be negative and constant, meaning that the slope for this diagram should be coming downwards and also be constant. So we have a straight line going from 80 back to 0, which brings us back to equilibrium, and everything's in order with this problem. So I hope this helped. If you have any other problems that you'd like to ask me, feel free to reach out in my email. And thanks for watching.